I'm Alex Turner, and today I'm going to talk about some work from the Beacon project at UC Berkeley, led by Professor Ron Cohen's group, that was recently published in GRL. Specifically, I'll be talking about our work using a dense, low-cost network to observe CO2 emission changes induced by the COVID-19 global pandemic. The work I'll talk about today is going to focus on the San Francisco Bay Area, and this background image is the Bay Bridge in San Francisco. I find it striking because it's totally empty, like many of the roads were during the peak of the shelter-in-place orders. The question we aimed to address was, what are the effects of shelter-in-place orders due to COVID-19 on urban CO2 emissions? San Francisco is an ideal city to examine, as it was the first city in the United States to implement such a shelter-in-place order. And the order was enacted on March 16, 2020, or about 268 days ago. Because it was the first city in the US to enact such an order, we might expect the most abrupt response here. Now, before I get into the specifics of the changes observed during COVID-19, I wanted to talk about how we actually go about estimating emissions. And there are two methods that I'll briefly discuss, the bottom-up method and the top-down method. The bottom-up method can be thought of as an accounting method. We take some activity data, such as the map of traffic density and emission factors, like the CO2 emitted per car, and the product of the two gives us a map of CO2 emissions from traffic. This method is great because it relates the CO2 emissions to the underlying processes driving those emissions. However, it requires a lot of detailed information at high spatial resolution and requires assumptions about how representative those emission factors are. In contrast, the top-down method attempts to back out the most likely set of emissions given a set of atmospheric observations. This cartoon on the right gives a simplified schematic of how this works. Briefly, we use a transport model to simulate what our measurements should see and then scale the emissions so they best fit the observations. This top-down method is often used in conjunction with the bottom-up method, or that is to say, we use the bottom-up as a starting point and then try to find where the bottom-up is over or underestimating emissions based on the atmospheric measurements. Our group has spent quite a bit of time putting together what we think is the best bottom-up estimate of urban CO2 emissions in the San Francisco Bay Area. In a moment, this animation on the left will show what our emissions look like. The top row shows a spatial map of the emissions over the region, and the left panel is our entire domain, while the right panel is zoomed in on the San Francisco Bay Area. The bottom row shows the emissions from different sectors over a week in March 2020. Black is the total emissions, orange is traffic, purple are stationary anthropogenic sources, green is the biosphere, and the background shading indicates daytime and nighttime. Our biosphere estimate comes from measurements of solar-induced chlorophyll fluorescence, or SIF, from the Tropomi satellite. Not surprisingly, we see large uptake of carbon from plants during the middle of the day. The important point here is that the biosphere estimate is not simply a prediction from a model, but actually constrained by measurements. We also see a daily cycle in the traffic emissions, and this comes from a high-resolution traffic inventory that was put together by Brian McDonald, who's at NOAA. The emissions from traffic can be clearly seen in the top right panel as the purple lines. Putting it all together, we see a sawtooth-like pattern in the daily cycle of CO2 emissions over the Bay Area, with the biosphere offsetting much of the midday emissions from traffic, and structural differences between weekday and weekend emissions in the Bay Area. So our aim here is to improve on this bottom-up estimate shown on the left using our atmospheric observations from the Beacon network. The Beacon network was established in 2013, and the aim was to blanket a city with low-cost sensors. Our instruments include measurements of CO2, CO, NO, NO2, ozone, and PM, but for this work I'm focusing just on CO2. We currently have more than 70 sensors around the San Francisco Bay Area, and of those, 35 sites were operational during the beginning of the shelter-in-place order in spring 2020. And the image on the left shows the location of those 35 sensors that were operational during this period. What I'm showing here are the measurements from all the Beacon nodes from January to July 2020 on the top as different colors, and the number of active sites on the bottom panel. Our group did some site maintenance on the network at the beginning of the year and, rather fortuitously, got many of the sites back online in mid-February before COVID-19 shutdowns occurred. The gray bar indicates the first week of shelter-in-place, and for this work, I'm going to focus on two time periods, 6 weeks before shelter-in-place and 6 weeks during the order. What I'm showing here is the median CO2 concentration across the network before shelter-in-place in purple and during shelter-in-place in green. Some of the most notable differences are in the middle of the week, particularly in the morning and evening rush hour. For example, on Wednesday morning we see about a 50 ppm difference between the before and during shelter-in-place order. However, some of this difference could simply be due to changes in the biosphere or meteorology. So what we're seeing is a clear decrease in CO2 concentrations, but still begs the question, how much of this is actually attributable to emissions changes? All right, now we're going to try and estimate CO2 fluxes using those beacon measurements. Our goal is to estimate hourly CO2 fluxes at 900 meter resolution across the San Francisco Bay Area during COVID-19. To do this, we're going to use Bayesian inference, and we'll walk through a couple terms in this expression here. The first term is XA, or the prior emissions. In our case, it's the bottom-up inventory I showed earlier, and here's a panel from that figure. So this will be our starting point. Y is our measurements. In this case, we'll be using those 6 weeks of observations before and during shelter in place. And H is the footprint matrix. This matrix encapsulates all of the atmospheric transport. So the way we construct this is using the STILT model, or the stochastic time-inverted Lagrangian transport model. In short, what we do is we advect 1,000 particles 72 hours backwards in time using meteorology from the NOAA High-Resolution Rapid Refresh to see where those particles came from. And we do this for every measurement, and we can use these back trajectories to determine the region our measurements are sensitive to. So what I'm plotting on the left is the cumulative sensitivity. So darker colors indicate a stronger network sensitivity, and the whites mean that these areas have little influence on our measurements that we make in the atmosphere. Zooming in on the San Francisco Bay Area, we can see the strongest sensitivities occur in the vicinity of our instruments, which makes sense. And this white line I've shown in the right panel encapsulates the top 40 percentile of the network sensitivity. We consider this region to be the region that we can actually constrain with our measurements due to the high sensitivity. This is important because, as you can see in the equation above, the posterior solution will simply revert to those prior emissions, XA, in the regions of low sensitivity. So while we would obtain a solution, it would simply reflect the bottom up, not the measurements, whereas we have confidence in the observed changes within this white region. All right, now I'll move on to the results and show the CO2 fluxes inferred from our measurements. Here I'm showing the spatial patterns of the posterior fluxes before shelter in place on the left and during shelter in place on the right. We're strongly sensitive to the East Bay, and the hatched areas indicate regions of low sensitivity, as I mentioned. We do see changes in the biosphere from the hatched areas, and those changes are actually constrained by satellite measurements of SIF from Tropomi. Most of our measurements are weakly sensitive to the biosphere, with the exception of the north shore of Richmond that I've pointed out with the arrow, where we do see a dominant biosphere signal in the urban area. This panel on the right shows a true color image from Landsat, where we can see vegetation dominating the coastline here. This second arrow points out the Chevron refinery in Richmond, California, and highlights some of the complexity of sources in the San Francisco Bay Area that we seem to be resolving in our posterior fluxes. You can see both the biosphere and the Chevron refinery in those posterior fluxes on the left. The panel on the right shows the difference between the two time periods. We observe large changes over the urban core and crucial commuter freeways, such as I-880 that goes north-south along the western shore. So the data suggests that the changes in urban emissions are driving much of the differences in our atmospheric measurements. We can also look at the temporal changes in the CO2 fluxes. The panel on the right shows the CO2 fluxes before shelter in place, and we're finding large CO2 emissions from traffic in orange that coincide with the morning rush during the middle of the week. This is not simply driven by our prior emissions, and it's notably absent from the weekend. The bottom panel shows the same thing, but for the time period during shelter in place. We see a 30% decrease in the fossil fuel emissions, with most of this coming from traffic and a small change from stationary anthropogenic sources. Two particularly interesting findings are the changes to the diurnal patterns. We no longer see those large rush hour emissions, and the nighttime emissions show a dramatic decrease. This is pointing to a major shift in both when and where our CO2 emissions are coming from. Finally, we also see a much more active biosphere, which highlights the importance of using measurements to constrain that signal. In summary, we're finding a 30% decrease in urban CO2 emissions in response to COVID-19 mobility restrictions that is primarily driven by traffic. These findings were only possible because of the dense sensor network employed here, and it really highlights the power of being able to get to these high spatial resolution patterns and separate the different sources. Finally, this work provides a glimpse into a world with reduced emissions from an electrified vehicle fleet. I've also included a few additional details about the inversion here, and feel free to contact me at the email address provided or check out the GRL paper. Thanks.